This is V 1647 Ori, which is a protostar. This was an observation with Chandra and XMM Newton and Suzuki, and it is a very, very young protostar. It is rotating in less than a day. And because it is rotating so fast, it has a lot of magnetic field lines, and there are disconnection events. And so we see a lot of X-ray flaring from this protostar because of those magnetic reconnection events, just exactly the way it happens on the surface of the sun. Except remember, this is a protostar, and it's going to take another 10 million years before hydrogen fusion begins in this protostar, and it's still putting out this amount of high energy radiation. What happens when these huge X-ray flares take place, it produces a shock wave that then moves out through the gas and dust, the little nebula that's surrounding the newly forming star. And that shock wave moving through that gas and dust kind of pushes a lot of the gas and the dust and the materials toward the outer edges of the cloud. And this is a good thing for planet formation, because if this didn't happen, all of that material would just infall and become part of the mass of the star itself. This is the scenario that sets up planet formation. And as we go along, and you look at these illustrations and these animations, remember that scientists cannot do science without art, because without the art, without the illustrators and the animators to show these really complex scientific concepts, it would be pretty hard for us to imagine them. And speaking of planet formation, this is an exoplanet. This is CoRoT 2a and CoRoT 2b. Sun and a hot Jupiter exoplanet. This particular planet is having an effect upon its parent star. It's actually increasing the magnetic field of the parent star. And in retaliation for that, the star is producing more and more high energy radiation, which is then evaporating the planet away at the rate of 5 million tons per second. So this is actually not a very good survival path future for this particular planet. On the other hand, just the opposite can happen. This is WASP-18, and this is another hot Jupiter planet. It's orbiting really, really close to its parent star. Hot Jupiters are usually less than 0.5 AU from their parent star. And this one is having the opposite effect as relating to the CoRoT system. In this one, this is a 10 Jupiter mass size exoplanet, and it is orbiting the star in less than a day. And it's actually changing the internal structure of the star and decreasing its magnetic field so that the star actually looks like it's older than it actually is. This is the part of a survey of 35 planetary nebulae. Now, planetary nebulas are the end products of sun-sized star as they evolve through their sequence from formation to their end products. The sun will end up producing a planetary nebula with a white dwarf in the center. Planetary nebulae are always very young because the material slowly radiates further and further away into space and gets more and more tenuous, and after about 50,000 years they're not visible anymore. And then all you have left behind is the white dwarf by itself. In this particular survey, Chandra was looking at the shock waves, high energy X-ray producing shock waves as they moved from the white dwarf through the planetary nebula, and what effect they had on the nebula and on the companion stars. Because just about all of these planetary nebula, they did detect the companion stars. These are all more massive stars than the sun. These are the result of stars that are massive enough to undergo a Type 2 supernova event. That leaves it leaves a supernova remnant behind, which lasts a lot longer because there's a lot more material involved with them. and the stellar core can either be a neutron star, a pulsar, a magnetar, or a black hole, depending upon the initial mass of the star. This one here is Cas A. We'll be talking more about Cas A as we go along, and we're also going to talk some more about the Crab Nebula, which is another Type 2 supernova remnant, all core collapses of massive stars. All of these in this image are in the Milky Way galaxy. These 6 Type 2 supernova remnants are in the large and the small Magellanic Clouds, 160 and 190,000 light years away. These are Type 1A supernova remnants. These are the result not of the core collapse of a star or the collapse of a star, but this is the result of the thermonuclear explosion of a white dwarf. If the white dwarf is in a binary star system or a multiple star system, as most stars are in those kinds of systems, they're not solitary like the sun. The vast majority are in multi-star systems. If you have, for instance, if you have 2 stars and one of those stars is more massive than the other one, it fuses its hydrogen to helium faster than the other one. It starts through its evolutionary sequence much sooner than the other one and ends up with a white dwarf, and then its companion star starts to go through its planet, its evolutionary sequence, and it gets to the red giant stage. So now you have a red giant with very loosely held outer layers because it's very largely expanded, right next to a white dwarf with a very extreme gravitational field. So the gravitational field of the white dwarf can, if the 2 objects are close enough, actually make contact with the red giant star and start pulling that outer atmospheric layers off the red giant star onto the surface of the white dwarf. And a white dwarf, if it exceeds Chandrasekhar's limit, which is 1.4 solar masses, then the electron degeneracy pressure can no longer withstand the force of gravity, which is always trying to contract the star and make it smaller. And so if this material that it's now accreting around it from the red giant, if some of that material drops onto the surface of the white dwarf, it sets off a little thermonuclear event, and that's what we call a nova. But if enough of that material drops onto the surface of the white dwarf so that the mass of the white dwarf starts to approach Chandrasekhar's limit, that sets off a runaway fusion reaction in the core of the white dwarf that literally explodes the star in a thermonuclear explosion. So the remnant is everything. There is absolutely no stellar core in a Type 1A remnant. These 3, this is Tychos Supernova remnant, we're going to talk about a little bit more, and Kepler's, and this one, 2010, they are in the Milky Way galaxy. This is DEML 71, which is in the Large Magellanic Cloud. Here is Tycho's supernova remnant, which we know he observed in 1572. It is all the debris from the white dwarf is in the center. The blue around the outer edge is the shock wave from the event. And right here is this odd little kind of a shock wave looking little curve. Well, on further study of this object, it has been determined where the actual site of the explosion was, and that little arc of material is actually material that was blown off the surface of the companion star when the white dwarf exploded. And on the other side of that of the material stripped from the companion star is the debris shadow. So from that, since this was the position of the explosion, here is the debris and the debris shadow, then the companion star had to have been between those 2 when the event happened, and from that it can be determined the direction that the companion star went due to the explosion, and they have found the companion star for this particular Type 1A supernova event. This is I love this image only because this I mean, how bizarre is it that you're actually going to get an image that contains both a Type 2 and a Type 1a supernova remnant together? Now, they didn't happen together, of course, because it takes at least 10 billion years for a white dwarf to form, and then a few more, astronomically speaking, a few more years, hundreds of thousands, who knows how many, before it actually becomes a Type 1a supernova event. And a Type 2, of course, is a core collapse of a more massive star, and they're much, much younger. You know, we're talking hundreds of millions of years instead of billions of years. So these two did not happen simultaneously. They're not really running into each other. It's an optical alignment illusion from our perspective here on Earth, but it's still pretty cool.